Hi everyone, welcome back. Today we're doing binary search. For our viewers that are new to the concept of binary search, we use binary search for finding a number in a sorted list of integers. It can also be characters, but in this case, let's use it in the context of integers. So if we have a sorted list, then it is possible for us to reduce the search space by half by taking the center element of the sorted array as the search space and comparing that number to, let's say, a target integer that we want to find. So if the number at that current position in the middle is currently less than the target, then it means that our number is probably towards the other right side of the search space. So by doing this binary search by taking the middle value and comparing that with the target, we are effectively reducing the search space by half every time. So this allows us to have a log n search space time complexity, where n is the size of our given sorted integers. So for this question, we're given an array of integers nums, which is sorted in ascending order, and an integer target, and we have to write a function to search target in numbers. And if target exists, we return its index, otherwise we return -1. And as hinted by the question, we must write an algorithm with O log n runtime complexity. So this is hinting to us to use binary search. So given an example like this array is sorted ascendingly, we have to find target 9. So in this case, because 9 exists at index 4, we return 4. For the second example, we are given the same sorted numbers as well, but we are given a target that doesn't exist in the list. So in this case, we return -1 since there is no index that contains 2. So for the constraints, the number's length range from 1 to 10 to the power of 4. Every single item along with the target, it ranges from -10 to the power of 4 to 10 to the power of 4. And all the integers in nums are unique, and nums is sorted in ascending order. So to do this, we'll be implementing our own flavor of binary search, and we'll be using this test case as our example. So we'll be tracing this together with our algorithm. So the first step is to define our search space, our initial search space. So we can represent our initial search space by defining a left and a right integer index, and this represents the indexes that we will be performing binary search on. So let's define a left, like its name suggests, that's the left index of our search space. So we will set that to 0, that represents the start of the list. We also define a right. In this case, this will be the length of numbers -1, and this is the final index in numbers in this case. So once we're done, our current condition is while left is less than equals to right. In other words, as long as our left pointer is continues to be on the left side of right or the same index as right, then we are still in the midst of binary search. So spoilers alert, by any chance, if your left index is unexpectedly more than right, it means that we have completed binary search, but we were unable to find any element that matches the target. So this is pretty much saying, well, the binary search is still ongoing. So once we have this condition, we will get the middle index that is smack in between left and right. And we will take that item at this index and compare it with the target every time. So to do that, let's define the middle index. The middle index will be left plus right, and we will take the floor division of that. So this operator, this double slash operator, takes the floor division. So if left plus right is 9, the floor division of that would be 4. So in this case, we will take the center element. So once we are done, we can compare if our nums at this middle index is equals to the target. And if that's the case, it means that the middle index is the index that we're looking for. So we'll return mid. Else, if numbers at mid, this current number that we're looking at is less than the target, then what this means is we have effectively slashed our search space in half, and the number we're looking for is somewhere towards the right side of our search space. So in this case, to prepare ourselves for the next iteration of binary search, we will set left to be equals to mid plus 1. So the subsequent iteration of binary search will take the right side of our current search space after halving it, and we will use that smaller search space to look for the target. Else, if the numbers at this mid is more than target, then in this case, what this means is we should take the left side of our search space after halving it as our subsequent search space. So in this case, we will take right to be equals to mid minus 1. And once done, we will return -1. So by any chance, if we reach line 19, it means that the number doesn't exist. So now that we have a binary search algorithm in place, let's try tracing this out with this test case over here. So left is now equals to 0. Right in this case will be equals to 1, 2, 3, 4, 5, 6. We have 6 elements. So right will be 6 minus 1 equals to 5. So I'll set this to 5 and let's continue. So in this case, this is true. 0 is indeed less than equals to 5. So we continue on the first iteration. So mid will be equals to the floor division of 0 plus 5, and this gives us 2. So nums at 2, this is equals to 3. Is 3 equals to 9? In this case, this is false, so we will skip this. In this case, the middle element is indeed less than 9, so this is true. So for the next iteration, we will set left to be 2 plus 1. So left is now 3 over here. So now left is still indeed less than equals to right, so this loop continues, and now our middle is now the floor division of 3 plus 5, giving us 4. So now we check the element at 4, 0, 1, 2, 3, 4, and that indeed gives us 9, and this is true, and we return 4. And the answer is 4, I guess. Yep, the output is 4. So this is a good demonstration of our implemented binary search. So let's run this against some test cases. This works. Let's submit this. And there we go. We completed this question. So let's quickly do a time and space complexity analysis. So currently, as we can see, in this case, the number of while loops that we have will be approximately O log n, log base 2n for our viewers who are curious. So the reason is because every time you do this binary search, we are effectively halving the size of our search space. And in this case, our search space is n, where n is the length of numbers. So because of that, the number of searches that we need for binary search is O log base 2n. For the space complexity in this case, we do not use any linear copies of numbers. So we only use constant number of variables, and these variables do not scale with the size of n. So space complexity is O1. And that's pretty much it for this demonstration. If you like this, please give us a like and subscribe, and we will see you in the next video.